Let's get started since we have a full house. Hi, everyone. Welcome to our Data Matters seminar. I'm pleased to introduce our speaker, Dr. Brenda Rubenstein, who's an associate professor of chemistry and physics, and also our incoming director of the Data Science Institute. We're very excited to have. Her research is focused on developing new electronic structure methods and rethinking computing architectures and computational biophysics. She was a Lawrence Distinguished Postdoctoral Fellow at Lawrence Livermore National Lab. She received her Bachelor of Science in Chemical Physics and Applied Math here at Brown, her MPhil in Computational Chemistry at the University of Cambridge, and her PhD in Chemical Physics at Columbia University. So very interdisciplinary work. We're excited to hear from Brenda. And so welcome.
Thank you, Carrie-Anne. Thank you for the introduction. And thank you to all of you who've come today. I see old friends, young friends, lots of friends. Thank you for coming to the Data Science Institute if you haven't been here before. I look forward to working with many of you over the course of the next few years. So today what I wanted to talk about is some of our more recent research in the group, which is looking at how we use quantum computers to model biology. And so I'm showing a small reaction that mimics ATP hydrolysis that we actually run using different kinds of quantum data. This is a long story. It's a complicated story, but one of the key layers of this is that you actually have to use data to make this happen. You have to use machine learning to make this happen. And so here what I'm doing is I'm running what's called a molecular dynamics simulation. So this is a simulation of just how atoms and molecules move. And why would we want to know that? It's because if we actually want to drug different things, if we want to understand how different proteins function in the body, we want to understand how these reactions go on. But historically, it's been hard to do some of this molecular dynamics, particularly if quantum mechanics matters. So I'm a Brown graduate. Rich taught me everything about classical molecular dynamics. Maybe Dan back there has also taught me a lot about protein evolution. But if you care about quantum mechanics, you might want to rethink these systems and potentially how you model these systems so that you can actually get these reactions right quantum mechanically. And so that's what our group has been trying to do over the past few years. So what is the motivation for this? And so you might say, why would you want to model bio on a quantum computer? And many people would say, does that mean you're doing quantum biology? So people know what quantum biology means. It's a term coined by Seth Lloyd and a few other people about maybe 20, 30 years ago. People would think about, well, maybe there's quantum mechanics that's orchestrating all of our neural networks and allowing us to think and have consciousness. No, unfortunately, I'm not talking about that quantum biology. So it's kind of the same as unlocking your quantum biology here. That's as much as I believe in that. But there is a lot of quantum biology that actually does go on in our bodies when it comes to different kinds of reactions. So here what I'm showing is something called an iron-sulfur cluster. These occur in enzymes called nitrogenases. And in these nitrogenases, you have these iron, essentially I'll call them bonded to the sulfur atoms. And because of that bonding, they have very, very complicated electronic states. The fact that they have a very complicated set of quantum mechanics that people would say is highly entangled makes it very, very difficult to understand these systems. Yet people want to understand these because these enzymes are the key enzymes that take N2 from the air and really convert it ultimately to things like ammonia that we can actually use. And so there's actually a lot of quantum mechanics that goes on in these kinds of systems and these reactions. And I'll even argue, even if you care about smaller, perhaps more basic reactions, there's also a lot of quantum mechanics that goes on. So here's the reaction that essentially powers you, I, everything else that we know biologically. So this is ATP hydrolysis. You take ATP, plus I'll say one water, and that goes to ADP plus phosphate and free energy. And so this reaction, by breaking a phosphate bond, so if you look over here, we have ATP, and here are some phosphates with oxygen, right? And if I break these bonds, here you see it's broken, this releases the free energy that really powers our bodies. And if you want to understand this process, this reaction of how we break that phosphate bond, then you also have to understand quantum mechanics. This is actually a highly complicated reaction that I'll get back to in a second. But the point is that on a small scale, quantum mechanics actually does matter for a number of processes biologically. And we want to be able to describe these processes accurately so that we can drug and do a variety of other different things in biomolecular systems. One thing that someone might say is if you want to understand these quantum mechanical processes, why don't you use a quantum computer, right? So if we have trouble simulating these kinds of things on a classical computer, which to some degree we do, why don't you actually put these reactions on a quantum computer? So we say yes to that, but let me just say, quantum computers can't actually do anything right now. This is actually Michio Kaku crying. I don't know if people remember that there was this article that NASA shut down its quantum computers because they were going to destroy the world or something. They didn't destroy the world. He's still crying. I'm crying because they still can't do very much. So quantum computers can't quite solve this problem, at least on their own right now. And I can go into all the reasons why I think they can't actually do it right now. But potentially in the future, they could. And with help, they actually can solve a variety of problems. So what I'll tell you is how data science and machine learning can actually contribute to solving these different kinds of problems and may actually accelerate our path towards quantum computation. One thing I should definitely say is I'm a believer that quantum computing plus ML is going to be the way that we move forward. I just don't see them separating moving forward. And I'll get back to that towards the end of the talk. So I'll start out by giving a brief introduction to quantum computing. If I gave a long introduction, I'm happy to answer any questions. If I gave a long introduction, we'd be here until midnight. I'll talk about some useful quantum computation that we can do using different kinds of force fields. I'll get into one example of data-driven quantum simulation, which is the modeling of ATP hydrolysis that we've been working on. Then I'll talk a little bit about the marriage of data and quantum. I should also thank the larger team that contributed to this. So I shouldn't say, I'm the only person. So this is part of a larger Wellcome for Bio grant. So Wellcome was very much interested in how you can actually use quantum computers to model biology. This is a team of electrical engineers, computer scientists, and a variety of statistical physicists. We all came together. I really drove some of the statistical physics and the electronic structure to make this happen. And I should also thank some of the people in this room. So I think Chi's there. Those simulations were from Chi. Our postdocs and trainees are essential to getting this all to happen. All right. So quantum computation, I think many of you have heard all the headlines. It's the future of everything. It will change everything. It will take us into another century. We can solve everything. I particularly like the fact that all of these different quantum computing companies say that there are 8 billion reasons to build a quantum computer because we're all going to have our own quantum computers in 2023, like they predict. And they also say that we're going to solve easy problems, which happen to be food insecurity and climate change. Just simple things. But they all say, importantly, that chemistry and materials are key targets for quantum computation. And so one key thought about quantum computing, even though quantum computers might not be able to give us much right now, is that they should be able to transform the space of simulating reactions. Reactions are quantum. It's hard for us to simulate them. I can give you a long story about that. That's what I spend most of my life doing on classical computers. But if there's quantum computing, we should be able to solve these kinds of reactions. Let me get into what quantum computing is and give you a little bit of a brief primer. The inherent bit of a quantum computer is what's called a qubit. So we should kind of set this up by talking about what regular classical bits are. So as we know, in classical computation, we work on classical bits, which give us one of two choices, right? They can be a 0 or a 1, and that's it. Two discrete choices. Just like a coin flip, hopefully not a rigged coin of some sort, but just like a coin flip, you get two choices. In quantum computing, we use what are called qubits, and qubits are an interesting combination. They're an interesting play on bits. So in qubits, what we do is construct a wave function from two different states. We typically call these states, let's say 0 and 1. I'll get into what those might physically correspond to shortly. But the key thing about qubits and the key thing about quantum mechanics is that these wave functions combine these bits with different amplitudes. So this A and this B essentially control how much character of each of these two states that we have. And so because we're actually combining two states, we can have this weird principle that we sit between a 0 and a 1. It would be a strange coin. It's always between 0. I don't know, maybe it's tilted, something like that. But a qubit actually sits between two different states. And that's called superposition. So somewhere you control what these A's and B's are. These A's and B's can be represented essentially as a vector. And on this sphere, you'll have your wave function. And that wave function can essentially point in different directions based on this A and B. Now, what's very important is that this means that these two states are in a superposition. So at any given time, we're in some combination of those states. And until we measure, we don't know which we're essentially in. And we don't know the probability that we're in them. This superposition is key to quantum computation. The fact that we can actually be in these two states in some sense at the same time is key. What this means architecture-wise is I think we're familiar with bits, right? Those are given by different kinds of field effect transistors. We can get a 0 or 1 based on voltages. For a qubit, we need to have those two quantum states. We need to have the ground state, let's say the 0 state, and the 1 state. We have to have 2 states. We have to be able to ensure that somehow a system can go between those 2 different states. And so the way that we do this, and there are many ways, and one thing I should say about quantum computing is we still don't know what architecture is really the best. Some of us have deep opinions about which architectures are the best. Some of you may have read the Microsoft headline about their topological qubits that just came out on Thursday. So they think now they have another platform for computing, although they didn't show any computing at all. So don't believe that if people told you that. So there are many platforms for qubits. The first and probably the most common, and what I think is probably going to win the race, is what are called superconducting qubits. And these qubits have 2 different states, essentially based upon the kinds of currents you can get through superconductors. So there are lots of, actually there are 4 or 5 different flavors of these superconducting qubits, but their qubits are represented by different kinds of current patterns or capacitance patterns in these superconducting qubits. A second technique, a second kind of hardware is called the ion trap. And this is the kind of system that most of us imagine if we're chemists or physicists. We want 2 states. What we can do is we can take a bunch of ions, they're also atomic versions of and we can essentially excite these from one lower state to one higher state, from the ground to the excited state. We can do it for all of these different kinds of ions. There are actually multiple different kinds of states that you can use here, but there just have to be 2 states that we can go between. And there are multiple other different kinds of architectures out there. People have thought about using nitrogen vacancy centers. I think Vesna physics would kill me if I didn't mention nuclear spins, which is one of the first ways that people did quantum computing. We can talk about why that doesn't scale. But anyway, there are a variety of architectures, and these architectures all have what we call 2-level systems. You have a 0 and 1, and we can make a superposition of the 2. So the way that we actually compute using these kinds of systems is by setting up different kinds of what we call quantum circuits. These are abstract because we want to abstract away the different kinds of physical substrates that are. But the idea is that you essentially set up your qubits with a here beginning. You have a number of qubits, you set them up, you compare them initially in state, and then you perform these little boxes. These boxes are what we call gates. These gates manipulate the qubits in different ways. You can think of these gates just like different operations that you might perform on a classical computer. And so there are many different kinds of gates. The simplest kinds of gates are called 1-qubit gates, so they just change 1 qubit. Change that vector that we saw is for a single qubit. But very importantly, what you need for computation is you need to have what are called 2-qubit gates. You see this line is 1 qubit. This line is a 2nd qubit, and these gates connect the 2 qubits. That means they're actually entangled. And entanglement is a key feature of computing. If things are not entangled, then you basically won't get any acceleration versus classical. And so these gates essentially say, for example, this gate would say, based on whatever state Q3 is in, I'm going to do something to Q4. So you can put these different gates together and map these to different computations. The way that people like myself or people in my group would do is we'd start with some, let's say, large problem we want to solve, and we transform it into these different kinds of gates and then work those on the different physical systems that we care about. One more thing that I should add about this, so this is just the kind of circuit that you would run, this piece over here, is that oftentimes classical computers are very much in the loop here, and I'll show you an example of that with our work. If you just ran these, you get maybe one answer out, maybe. But the point is that you have to measure these. So there are many, many measurements that you have to do in order to figure out exactly what the answer was. And so this is a little bit weird compared to classical computing. Usually, you get a number, it's a number, and usually there isn't a high variance on that number. I mean, maybe at the physical level, there's some variance, but for us, for the most part, there isn't that much variance. But for a quantum state, it's probabilistic. Quantum mechanics is probabilistic. you have to measure and measure again and measure and converge those errors. It's kind of like trying to sample random numbers to some degree, random probability distributions. And so then based on those measurements, you'll get an outcome. And since a quantum computer can't do everything, I mean, this is really what a quantum computer can do. It can solve what we call a given Hamiltonian. So it can solve a problem that's encoded in some way that acts on these different qubits. Once we measure what happened there, then we need a classical computer to go and do other things to remanipulate the computation. So most commonly, a classical computer is going to reset up what gates we want to run so that we can maybe converge our answer better and do it again and do it again and so forth. So classical computers are almost always in the loop for all these different kinds of systems. So there are a lot of steps in between. Maybe I won't bore you. Again, we'll be here until midnight if I talk about all of them. But one key thing I want to note is that what quantum computers have been able to do, and just like those companies focused on chemistry, they've done a lot of experiments in chemistry where they've looked at basically energies for different kinds of small systems. So let me emphasize small. So I know you might have heard that there are companies producing thousands of qubits. If you look at the IBM roadmap, they talk about thousands or tens of thousands of qubits. But really, all of these different kinds of chemical simulations involve less than 20 qubits. And I'd really say what's practical is more like 10 qubits. So these different examples here, this is what we call hydrogen chain simulation. They basically map a hydrogen atom to 1 qubit each. And then they were trying to figure out what is the energy of that chain as it starts. This is an example with H2O. And here with H2O, they're just trying to figure out what is the energy of H2O. That's it. And what I'll point out about all these different experiments, not just that they're small, is that they're also super noisy. And these are probably some of the better examples. So if I look at this H2O experiment, we're trying to get the energy of H2O. You see that there's quite a bit of fluctuations that are going around on here. The green is pretty wide. And so if you actually want to extract an answer, you have to spend a lot of time beating down the noise. And so where does that noise come from? There are a lot of potential noise sources depending upon the architecture of the quantum computer, but essentially they start losing information about what state the qubit is in over time. And so that messes up your calculation, to put it mildly. So there are a lot of interesting things going on in quantum computing. We have machines for the first time. That's exciting. We can actually play with these ideas, but they're still giving us super small calculations, very small. Anybody who knows about quantum computing, maybe one thing I should say is that single, you know what an orbital in an atom is? Single orbital in an atom, just like maybe a hydrogen orbital. People remember chemistry and know it's scary. The 1s orbital is 1 qubit. So if you want to do 1 orbital, that's 1 qubit. So if we're talking about 12 qubits, we're talking about like 12 atoms at best, if you use the minimal model. So these are super small calculations. You want to think about proteins, big things, we are not there yet. And there's a huge amount of noise that you have to get around if you're going to actually pull out an answer. So we still haven't pulled out an answer, at least in chemistry or biology, that's better than what we can do on a classical computer. Right now, we have not done that. So why do I say this? We get energies, but one point I want to make is that energies are only so useful, particularly noisy energies. What are we going to do with that? It's not super accurate. I can't go to my friends in chemistry and say, measure that on my spectrometer, because they'll say, well, I can measure that in 2 seconds and get an answer way better than you. They just kind of laugh at that. Energies are only so useful. And in most fields, what we really need are things like forces and dynamics. I showed you movement in the earlier images, the video I showed before. That's movement. In chemistry, physics, we usually care about things moving. In biology, we care about different conformations of proteins changing their shapes. That's how they function. So we care about movement. This is actually an interesting story of how we actually came to doing this work. So I'd say this probably started many years ago. I was working in Rich's lab many years ago, but I also used to work at Columbia. And some people in the audience would know who Bruce Byrne is. Bruce was trying to convince me to go work in his biology group, biophysics group at the time. And I said, I'm thinking about working on quantum Monte Carlo methods. And Bruce said, well, that's great, but you won't be able to do any chemistry. There are no forces that you can use in these kinds of methods. So these are a certain type of quantum method I was very much interested in. And so I said, I'll just do it anyway, even though he said you'll have no career and nothing. Ironically, Bruce is one of the first people to work on these kinds of methods. Now his whole department works on these methods. So anyway, Bruce has great intuition. Back then, the reason why I bring this up is that we actually also couldn't do forces in some other quantum methods that we ran on classical computers. And I remember that very well from way back when. And so forces are actually super important if you want to do real things in chemistry and in physics. I'll give you a couple of examples as just a reminder if you don't know why. So here's a protein that my group has also been working on. It's called ABL1 kinase. A kinase is a protein that phosphorylates other proteins, essentially turning them on. And this kinase has very interesting motions. Oh, I guess I can no longer play the file. Anyway, this kinase can have interesting dynamics. And in specific, if this group here is called a DFG group, goes in or out, it controls whether this kinase can actually phosphorylate. It can actually move a phosphate group onto another protein to turn it on. And so dynamics is very important for this kinase. For example, for this kinase, people actually didn't know how drugs worked on it for a long time. So Gleevec is a popular drug that blocks these kinases. And people just knew that it blocks certain kinases, but not other kinases. So the kinase I showed you, it blocks really well, but some other kinases it doesn't block. It took them years to figure it out. And why? Why does it block this? It's because of its dynamics. So this particular protein likes to sit in one kind of configuration that its ancestors actually don't sit in very frequently. And so dynamics matters for things like drugging proteins and understanding how they work. It also matters for things like ATPase activity. So if you want to drug different ATPases, it's super important. And it's also important for understanding reactions that involve these different kinases and ATPs. So for example, I'm showing a little bit of ATP hydrolysis I'll go into in a second. If you want to understand how this reaction works, that's dynamical. Things are moving around. You have to know how things are moving around. And so what we wanted to do is try to figure out how do we bring these quantum methods, which give us energies, and make them give us forces, make them give us dynamics, which is actually useful. Like energies themselves tend not to be that useful. And so we wanted to go and figure that out. And so ideally, if we could run things on a quantum computer and get really accurate energies for these systems and also be able to get their dynamics, then we could run a full protein, we can run a full reaction and understand exactly what's going on in these systems. But the question is how would you do that? So I remember back to this. There are a lot of strong similarities with some methods that I've spent my life working on. Expensive methods, noisy methods, can't get forces. And so what we realized is that we can actually learn different force fields. And so I'm taking this from Andy's paper. So Andy's here. Andy was one of the first people who really made me think about these different kinds of methods. So if you want to get dynamics, how do people get dynamics for proteins? So historically, what we've done is we've used Newton's laws. So if you calculate the energy of a system, the potential energy, you can take its derivative and it gives you a force. And then you can use Newton's laws to move things around. Like if you know forces, you know from Newton's laws, you have some positions, you move things forward, move things backwards, and things move in time. And so people have spent many years working on these kinds of what we call molecular dynamic simulations, where we move things around in engineering. So this is an example of vacancy formation, where you can see some of the atoms will move around and either create a vacancy or destroy a vacancy on the surface. But again, also super important in biology. So it's not showing the movie, but these proteins move around, super important for their dynamics. And the way people would get these dynamics is basically by calculating the energies of different configurations of these systems. So I'm showing here, this is just a piece of a protein. But what people have historically done is they've tried to figure out what the energy of these different pieces are as a function of, let's say, bond length, so if you stretch a bond, or distances between different kinds of atoms, or maybe how things twist in different ways. They construct these huge potentials and take the derivatives and they get forces. And that's, if you've ever seen movies of proteins, that's how we do it. That's how people have always done it. Now, what people also used to do is if they wanted quantum mechanics for these systems, they would literally sample every configuration. So if the protein stretched like this, they would calculate the quantum energy for that. If it's stretched like this, they calculate the quantum energy for that, and they do this, every single configuration, the whole dance. They would just keep calculating energies and energies quantum mechanically. Super expensive, because on a classical computer, it takes forever to do that. And so the smart thing that people like Andy and their some predecessors came up with is that they realized that they can actually train neural networks using data about these kinds of energies rather than calculate an energy again, and keep doing that. So the idea is that you can take different configurations, you can use them as a training set. These configurations are the coordinates of, let's say, atoms or molecules. You can feed them into a neural network. So typically people will take the configurations, they'll perform some symmetry operations, they'll feed them into neural networks, and then they'll get energies for different pieces and combine them into a final energy. So people have been doing that. Why would they want to do that? So now they don't have to repeat calculations again and again. Right? They don't have to run quantum mechanics a million, billion different times like they once did. And definitely in the 90s, people would do that all the time. Instead, you can train your neural network and it could tell you the energy. If I give you a new set of positions, coordinates, I can get the energy out and just tells you that automatically. Now, that gives us energy, right? But I guess what I realized working on this over the years is actually we can use this for a variety of purposes. It gives us the energy, but if I want forces, I can also just get forces from this network. And so that can solve a lot of problems. I didn't have forces in some of my other kinds of calculations. I don't have forces from a quantum computer right now. I can talk about all the details of that, but we don't have good forces from quantum computers. We just have energies. So we can train on energies, make these neural networks, and we can get forces by taking derivatives. And that gives us dynamics, and it gives us fast dynamics. We just need some energies, and then we can go forward and we can understand how things are reacting and things are moving. So I'll show you what I'll call the early stupid case. So we did some early work where we tried to understand how to do dynamics on little small molecules like these. All these things can do is they can vibrate. That's pretty much it. Nothing exciting. And at the time, we were actually using, this is Andy's software. Back in the day, we used that software. We have better networks now. No offense, Andy. Andy would say that. They're better neural networks now. The idea is we take molecular geometries, we do some quantum calculations, they give us energies, feed them into a neural network. That neural network would predict energies and forces, and then we can run a bunch of dynamics. And so we did that for these systems, and we'd be able to spit out really great energies from the networks. So these are some of our network results. These are some of our original inputs. We originally did this on classical computers back in the day. So we get the same energies essentially. Forces, we get mostly the same forces. We didn't train on forces, so it's actually not terrible that we didn't get exact forces. So we mostly get that, and we could run dynamics. So here again in the black, we have our original quantum calculations, and then in the other colors, we have other calculations from the neural network. We get roughly the same dynamics. But that was the stupid case. We asked if we could do better, can we do cheaper? Then we started to ask, can we do this with a quantum computer? So let me tell you the smarter way. And I think everybody now in the community has started using this way. And we were some of the first examples of this. So the idea is instead of training all of my making lots of big sets, what I can do is I can train a really cheap data. And for those of you who are in Mel, right, you'd say these are like foundational models. I can train some neural network on some foundational data that's cheap. And it doesn't necessarily relate that specifically to my system. And then what I can do is if I really want to do things efficiently with not that much training, I can use something called transfer learning to transfer into my network, meaning change the weights of my network a little bit. I can transfer learn in a few higher accuracy calculations that are specific to the system that I want. So I'm sure many of you have used transfer learning for a variety of things, but this really changed everything for us. So, originally a lot of our predictions were noisy and we had to do a lot of training. Now what you can do is you can start with a foundational model, then you can put a layer in of maybe cheap data on top of the original foundational model, and then you can put in an even smaller layer of really accurate data to improve your network and improve its predictions so that they're almost exact. And so we did this again on classical hardware, but what we realized is what we can do is we can also do this with a quantum computer. So now that we don't have to use that a large training set, so we don't have to use a lot of examples, maybe we can use 10 examples, 100 examples at most, we can instead substitute quantum computed energies, which if quantum computers get good enough should be exact, near exact. We can substitute those in and get an exact prediction from our network. So that was the idea. And so we did that, and we did that using also active learning. So for those of you who are familiar with active learning, instead of having sort of a static training set, what we do is we start with some larger data set, we sample some points, we train on them, and we train a committee of neural networks. So the field likes to use 8, but there's really no reason for 8. Maybe one of you can tell me why not 8. But we train 8 committees, so 8 neural networks, 1 committee. And that committee tells us the mean of what they predict for a given sample and the variance. And then based upon what that committee tells us, we can go back, and if the variance is high among those different networks, we can pick new data and retrain the networks so that we get even more accurate predictions and reduce that variance and keep improving. And so this is another way also to make our data sets super sparse so that we don't have to keep training, and we also don't have to make a super huge data set. So anyway, here's the big scheme. So this is how we're now doing dynamics on quantum computers. So we take data from quantum computers, but also from classical methods. We train our neural networks. We get these potentials. So these neural networks are telling us potential energy surfaces between our atoms. And then from that, we can run different kinds of dynamics and understand reactions, not just energies for the first time. And this is sort of the setup I was explaining before. We can transfer learn with we can start with a foundational model, then we can put in some more specific points, and then we can put in some super high accuracy but costly data points later. So we first decided to do this for water. We sampled a lot of water configurations. Water is the simplest case. You can run them on quantum computers. The idea with water, just one water here, simplest case for now. With water, you can stretch the bonds. So you can stretch the OH bonds in different ways, and then you can figure out what is the energy as a function of the bond distances. And you can also change the bond angle, so water can flap like this. And we can try to understand and see if our networks can give us the exact answer. This is a super small case. Water is small. Hopefully you're clear that water is small. Water is just one molecule. And so the blue here, we can do exactly, this is the exact calculation. So what we ultimately want is to get to the blue, but we can start with some, let's just say, foundational data, and that might be the red curve over here. We can see if we can get from the red to the orange there using these networks. And so if we do this, if we train and we do this transfer learning, in fact, we can't exactly get those kinds of answers. I'm purposely putting the error bars here so that you understand what's going on. So again, this coverage is the exact answer. The reading is where we started from with maybe some of our foundational learning. And then after we were able to do this learning, we get the blue. And what's nice about this is that since we have committees, the neural network committees, we can also see the variance on our answers. And this tells us, oh, we don't have to do anything. We should go and put more points. Turns out I don't care about the points here. This is super long chemical bond. If you know what it go, I wouldn't care about up here. You tell us, okay, spend more time here. Can we train our networks and do this iteration? So anyway, we can do this for small molecules. We can get pretty much exact dynamics. And so you can see the cute little movies. This is using quantum computed data, see how they work. What we can also do is actually look at reactions. And so that's what I was talking about. And so I'll end on some of these themes. So we can also look at things like ATP hydrolysis. I said we're going to do biology. So we're starting to do biology here. And one example is ATP hydrolysis. I mentioned that in ATP hydrolysis, what we want to do is we want to cut this OPO bond here so that we would release a phosphate. And historically, people actually don't know the kind of energetics for this. It's very quantum mechanical. It's hard to get the answer right. What's also hard is that People don't know what actually participates in the reaction. So there are lots of waters. People aren't sure which waters do what. They're also not sure about ions. So people think about phosphates. There are lots of magnesiums hanging around. People didn't understand that for a long time. And so people wanted to understand, how did this reaction go? How does it work? If you start with one reactant state, go to the product state, does it follow one path or another? And the two paths that people used to debate is, does a water come in and cause this phosphate to leave, or does this just kind of break by itself? So people didn't really understand. Well, we know is biologically how much energy this releases, but nobody's been able to quantum mechanically reproduce it. It's been very hard. There's a Nobel Prize that related to making the methods to even get close to this problem. And so we went in with a mimic for this that we wanted to run on quantum computers. We can't run all of ATP. We're gearing up to try to do that. A lot of tricks that we have to play for the whole molecule. So we made some mimics called metaphosphate, and we put one or two waters in it. We wanted to understand how these waters actually cause hydrolysis. And so what you can have is, in the one water mechanism, a water can approach the P and cause this to break, or you can have a water approach and then they exchange a hydrogen instead through a shuttle, and then cause the reaction to go. So we wanted to look at that. And so what we had to do is train lots of different energies to be able to go through these different pathways. So try to see how these waters affected the reaction. We had to train along different pathways and get lots of different data points, sample them, and make our foundational model. We had to do active learning to create that model and eventually generate a surface on which we can run the dynamics. And ultimately, and I can go into the details later, by doing this, we can in fact see how this reaction proceeds. And again, this is with quantum computed data. These energies, once we do our transfer learning, are based on quantum computation. And you can basically very slowly see how eventually this reaction happens. Right now, the waters are just playing with each other. But eventually, if you wait long enough, one of them will actually break apart. It's going. You got to wait a long time for molecular dynamics. It's getting there. Okay, there you go. And there was our reaction. So we see that we can actually do reactive dynamics on these computers, which is exciting, but super small system and not a lot of data so far. And so we're really trying to push towards, how do we do this for much larger systems, fewer qubits, with very compact circuits. And I can go into the details if you want. So in summary, hopefully what I've shown you is that we've used machine learning and data in order to use quantum computed energies. We've used a product of quantum computation and made that useful by trying to use machine learning to get forces and to do dynamics. And what we've been able to solve is just how do you deal with forces? How do you deal with the number of calculations that come from these quantum computers, and noise? So machine learning, neural networks are really good at getting through noise, from my experience. They can cut through noise in ways that regular calculations can't. But let me also remind you of the bigger picture. Again, I don't want to keep you here all night. This is just part of a larger frontier of using machine learning in quantum computation. So there are a lot of steps in quantum computing. Have to make hardware. We got to pre-process our data to run it on the quantum. Then we have to actually run our different kinds of circuits. We got to do something called error correction to bring down our errors. Then we got to post-process. I showed you that we used ML to post-process, but there are a lot of places where data and AI can help. They can help us make better hardware. They can help us actually prepare quantum states on a quantum computer in a dense fashion. So, we're not taking up a billion qubits. We can squeeze our problem down. We did a lot of work on that. I won't talk about it here. We also can use it to make sure that we're not producing large amounts of noise and to even do error correction. So all the recent papers that have come out on correcting these calculations on quantum computers have used different kinds of AI and data-driven techniques to cut through and do some of this error correction. So the point is that there are just lots of opportunities to use data science and AI to make these computers work. They give noise, they're small, they do small calculations. If you want to extend them, machine learning is going to be a very important part of that. And it's definitely something that's starting to happen in the field now. So with that, I'd like to thank everybody for their attention. I'll thank my group for all their help. So Pratik, I think he's not here, but Chi is here. Chi did a lot of this work. There's Chi over here. This work was funded mostly by Quantum Leap, but a lot of these ideas came from lots of earlier grants from AFOSR, NSF, and DOE. I'd also like to thank our larger team. We got a lot of help thinking about how do we do really good transfer learning from a great postdoc, Michael Chen. He wasn't on the faculty market, but I would have loved to hire him. And again, Pratik and Shi did lots of the work. And I'll just put a plug in because Alan's here. He said I have to. So if you're interested in quantum computing, got the Brown Quantum Initiative, great student group. They can teach you lots about it. Great. Thank you all.
So now we're going to do